All right.
It was like 2 weeks worth of math, you were gonna explain it now.
All right. So we were talking about standard deviation, which is a measure of dispersion. It's a standard measure of dispersion, right? And when you're dealing with a population, don't forget that variance and standard deviation are tied together. When you're talking about a population, you talk about sigma squared. When you're talking about a sample, we use S's, so it's S squared. All right, so this is just notation that you need to be okay with because it's something that will be used in every statistical study that you work with. They will always talk about sigma and S, and whenever you're talking about Greek letters, those mean populations. Whenever you're talking about English letters, those mean samples. So,
With that in mind,
I gave you the formulas, right? And I said, okay, sigma squared is the sum of all of your x's minus the mean squared all over n. And this is the standard definition of variance. Okay, it's the average square of the distance between your data and the mean. All right, so you're calculating an average over all of your data points. All right, and when you're working in a population, you can use n when you deal with your average. When you're dealing with samples, you have to take a slight twist. It's the exact same formula, except you subtract 1 from n. Okay. Now, the reason why you do that in a sample is because a sample, by definition, has a mean that you can calculate. And what we as statisticians say is that the last value of x in your sample, it is chosen to get the sample mean that you get from your data. And therefore that last data element, which you'd like to think is truly random, is not, because you use it, or it is used to force the mean to be whatever it's going to be. And therefore you have to ignore it when it comes time to calculate your average. That is my 2-minute hand-wavy explanation of why you do n minus 1 for a sample, but n for a population.
one more time.
Okay. So the idea here is that in a sample, you're going to have some mean of your sample. Okay? And the mean of your sample is a fixed parameter. So it's a known value for your sample. And because you have fixed that value, the last data element in your set of samples is fixed to also guarantee that your mean works out to be whatever mean you've set it is. Whereas in a population, the population mean is not being driven by the sample, it's being driven by the population, and therefore there isn't any non-element that you're working with. It's a entire population, so there's nothing that's being forced to be fixed in the population. But in a sample, there is. And that's why, from a hand wave perspective, you subtract 1 from it. You're essentially, what I'm getting at is that you're losing a degree of freedom in your ability to calculate your standard deviation. And that's why you subtract 1. Because the mean fixes one of your standard variables into a specific value so that you can get that specific mean, whatever it was for the sample that you took. Again, that's about as good as I can do, and I don't want to go any deeper because it's a really deep rabbit hole. It's fun, but it's scary as all get out. Okay, so just please keep in mind that when you are dealing with samples, instead of averaging your differences squared, you do a little bit of a twist and you take one away from the number of elements that you're working with, okay? All right, so those are variances. If you take away the square, i.e. take the square root, you're calculating the standard deviation as opposed to the variance, okay? So variances are squared values, and note these are squares, and so are the squares in my sums. And when you deal with this standard deviation, you will always take the square root of these things in order to get them, okay? So the notation is sort of directly telling you that variance is a squared parameter, standard deviation is a not squared parameter. All right. So So if your standard deviation or variance is larger, the more your data is spread out. Because again, that's what it's doing, is measuring dispersion, okay? All right, now, what I wanted to do before we move past it so what did I assign for homework in chapter 3? 3.2, let's see. Look it up. So 4, 8, 12, 16, 20. All right, so 8's such a good number. All right, so I'm going to do number 3 out of the book. It's not officially part of the homework, but it's a book problem so that you can get an idea of how the book questions are going to come at you. All right? So here's your data. 5, 6, 3, 5. 7, 7, 8, 25. And that's a 5, I swear. Looks like a scribble. All right. So in this problem, it asks you to calculate population variance and standard deviation. In other words, how do you use those weird formulas I just wrote up there a little bit? So how do we apply this sigma squared formula? the sum of the numbers minus the mean squared. So, what's one of the first things I have to do? Well, I have to take each one of these numbers and subtract the mean. Do I know what the mean is? Not yet. So the first step, whenever you're calculating variance and standard deviation, if you haven't done it already, calculate the mean. How many numbers are up there? 8.
That was one of my kids. I'm like, huh? Did I do something?
Yeah, there's one weird number there at the end, 25. Eight and a half?
I'm still working on it.
8.25?
Yeah.
Okay, sounds good. All right, so. Now what we need to do is to take each one of our data numbers, subtract the mean, and square it. To keep it a little bit cleaner, I like to make a table just because it keeps things clean. So put your numbers in here and put them in order so that it's easier to keep track, right? So I gave them to you in sort of a mixed up sequence, so order them, right? The lowest number is 3, then we get 2 5s, 1 6, 2 7s, and 8 and 25. So, in the next column over, do that subtraction, right? What is 3 minus 8.25? And then do 5 minus 8.25. And if the number stays the same, folks, please don't do the subtraction again. If the number's the same, the subtraction is the same, right? And the cool part about these is that hopefully, right, if we add 1 to 5, that makes it 6. We're basically adding 1 to the difference, so just add 1. You don't really need to do the subtraction. Another 7, negative 1.25, 8. And then last but not least, 25. 16.75. The reason I like to do this, folks, add all those numbers up. What do you get? Good guess, but not quite. When you add up all the negative numbers, what do you wind up getting? 16.75. So you've got negative 16.75 plus 16.75. You should always get 0. That's the definition of the average, right? It's the number that does this, right? There's one and only one number that does that. Bam, there it is. And now technically, what do we have to sum up? We have to square all of those numbers. Mildly annoying because you get lots of decimals, but a lot of them are repetitive. And note, folks, when you square a negative, what happens? It turns positive. Please don't write any negatives down on the squared section. That's the whole point, is to get rid of the negatives so that they don't cancel each other out. And the nasty one at the very end. A little bit ugly, but again, they're just numbers. You can add them up, right? And now you have a nice, easy way to add them up. 8 5s, 40, carry your 4. 8 2s, 16, plus 4, 20, carry your 2. 8 6s, 48, plus 2, 50, carry your 5. Not quite 8 of those, right? How many are there? There's 6 of them. 5, carry your 3. 10, 15, 16, 17. 7, carry your 1. 3, 4, 5, 13, 3, 37 and a half. This just makes it a little bit cleaner. And what I'm also trying to show you, folks, is that this would be an ideal spot to use a spreadsheet program, right? Because it's real easy to punch these numbers in the first column. And then all you have to do is tell it. Well, subtract whatever the average is right here. Repeat that formula all the way down. In the next column over, just tell it square that number. Repeat that formula all the way down and hit the button that says add them up. Okay? There's nothing wrong with you guys doing the standard deviation problems like that if you wish. Okay? If you want to use a spreadsheet program, you're more than welcome to. But this is also perfectly good. And when I was in undergraduate college, this is what I had to do. I had to do it by hand because none of those software packages were widely used back in the 80s. So I had to do it the hard way. So if you want to, by all means, please do. But don't feel like you have to. If you want to use a spreadsheet program, go ahead. All right? I'm assuming you're going to use your calculator, so what's the difference? All right? Now, we're not quite there, right? We want to calculate the population variance. So what am I going to do with that 337 and a half? Since it's a population, I divide by n. How many numbers were there again? 8. So 337 and a half over 8. Somebody punch that out really fast. What do you get?
42.1875.
1875.
42.
42?
Oh, yeah.
That is your population variance. What is your population standard deviation? How do you get rid of a square? Give me a bunch of digits just to start with.
6.49519052.
Second one is standard deviation.
Yes. Standard deviation is when it's not squared, i.e. you take the square root. Variance is when it is squared or you haven't taken the square root. Right? So variance, standard deviation. Now, let's see how we did.
Your answer's gonna be different. Your sum of the numbers was wrong.
But why did you say something?
I was just letting you go with it.
Yeah, if the sum is wrong, folks, what's the real sum?
It's 337.99375.
Really?
Yeah, I did it twice, and then I double checked the work by going back and making sure they were all accurate.
Huh, that's weird. Sure looks like that. I mean, it's close, right?
I may have made a move. Yeah, I think I did.
So, note, if you look at the answers in the back of the book for chapter 3, what does it tell you the population variance is? Tells you that it's 42.2. Now, why did the book round it to the hundredths, or to the tenths, sorry? It's like sig digs. But the general rule of thumb, folks, when you're dealing with your standard deviation and variance, always round to one decimal place past your data. So if your data goes to the ones place, round your variance and standard deviation to the tenths. If your data goes to the tenths, round to the hundredths, etc., etc., etc. Okay? So always add one additional decimal point for your variance and standard deviation. So in other words, when we said the standard deviation was all of those numbers, you should probably round it to approximately 6.5, okay?
I see where
There's a 7 in there somewhere.
yeah, well, almost all of them have 5625 at the end, except for
Two
the
of them.
number 6 where it's 5.0625. I put 5. Well, you know what?
Yeah.
That's-
All right, so any questions about the calculation process? All right? I mean, this is just a matter of doing the numbers, folks. I mean, it's a little tedious if you're gonna do it by hand. So just be ready if you know, there's like 4 or 5 of them where if you do it by hand, just, crank through the numbers. And then at the very end, note, folks, though, A lot of things that students will sometimes do is round the squares while they're going. Don't do that. Do not round anything inside of this table, only round at the end, okay? So even though there's 4 places over here to the right in our squares, keep them all and don't round until the end, all right? One of the things that you gotta get used to is rounding less instead of more. The more you round, the more you can generate rounding errors. So if you just round once, you have not generated any rounding errors, and that's good. All right. And how is this problem different if I told you it was a sample instead of a population? One, you would call it S instead of sigma. And what else would we do?
Divide the 11 by 7.
Yeah, we would just divide this by 7, but everything else exactly the same, okay? So samples and populations, you almost consider them the same thing. It's just that they are slightly different because of that little n minus 1 instead of n, okay? And again, please, when you're doing this chapter 3 homework, read carefully so that when it says population, use population. When it says sample, use sample, please. Okay. All right, so we're okay with the calculation values. All right. So, okay. What does that sentence mean? Standard deviation can be relative to the mean of your data.
So as the mean of your data changes, so does the standard deviation?
Yeah. Basically, as your means get higher, your standard deviations can look higher just because your numbers are getting bigger, okay? So what we need to do is sometimes normalize for the mean. The coefficient of variation basically is what you use in order to normalize out the mean, and basically all you do is take your standard deviation, divide by the mean, and then multiply by 100% to figure out what percent of your variance is based on the mean, or based strictly off of the mean, really. So it's just a way of calculating how much your variance or how much your standard deviation is compared to the actual numbers that you're working with. So So note both of these problems have a standard deviation of 2.5. But if the mean is 7, then our standard deviation actually is bigger than if our mean is 50. Because compared to 7, 2.5 is kind of a big deal. It's almost a half. Whereas 2.5 compared to 50, that's relatively small. And so this standard deviation here is actually considered to be less of a standard deviation compared to the actual mean, okay? So you can crank these numbers out and get a specific percentage if you want, whatever it works out to be. Somebody punch those out real fast. What's 2.5 over 7?
35.7.
Where's down below?
5.
So even though the standard deviations are the same, in this first example, there looks like there's more standard deviation compared to the mean because the mean is so small. Whereas when we look at the second example where the mean is 50, now the standard deviation is not as big a deal because our number is so big, okay? They both mean the same thing. The standard deviation is 2.5, and from a how different are your numbers perspective, it's the same. It's just that when you compare it to the mean, that may mean that, or that may imply that there is more going on than you might think by having the same numbers in these two problems. So again, it's just a matter of what does it mean in comparison to the actual average of your data. All right. Now, oh boy. So what do you do if you don't have the data and only have a grouped frequency table? So normally you know what to do when you have all of the information. You just do that little table that we created, add the numbers up, divide by the number of numbers that you have. There's your variance and standard deviation calculated away. So if you take a peek in 3.2, there is a formula in there that describes it. It is an ugly as sin formula. It's on page 118 in the old book. I don't know where it is in the new book. Sorry about that, folks.
Me neither. Yeah, I think I could.
That is a very scary formula, folks. F is the frequency of the group. X is the midpoint of the group. These sorts of formulas, folks, are the bread and butter behind statistics. There's lots of summing of products of squares, squaring sums after you have multiplied them together. So basically what this is saying, or what you're supposed to do in this kind of a problem is, in this first parenthesis, that summation basically says in each row of a table, take the frequency and multiply by the midpoint squared. Add the next row's frequency times the midpoint squared. Rinse and repeat for every row. That'll give you this number. Then you multiply by n, where n is the number of rows. Or not the number of rows, but the sample size. N is always sample size. And this other side of the equation, this other parenthesis with the summation, basically this just says take the sum of all of the frequencies times the midpoints. Add all of those up, and when you're done adding them all up, that's inside the parentheses. So once you have added everything up, then square whatever number you get after you add them all up. Okay? So this sort of notation is very common in the statistical world. You'll see it thrown at you off and on just to try and make someone look like they know high-powered math. But a lot of it is just formulas, all right? So, this one always scares me a little bit, so I think there's an example, because I know I asked you to do one on the homework. So do I ask you to do 20 or 22? 20? Yeah.
20.
All right, so let's do number 21. So really quick. .05 to .08, 7, .08 to .10, and 15, .11 to .13. There are 14. 1.4 to .16, 15, and .17 to .19, there are 14. So, how would we apply that formula to this set of data? So the first thing you have to do is find all the midpoints, because that's what X is telling you to use. So what is the midpoint of all of these? How do we do midpoints again? Quick review of chapter 2. Add them together, divide, was 0.05 plus 0.07 divided by 2. 0.06, and 0.9, 0.12, 0.15, 0.18. Something similar to, but not calculate the standard deviation of it. So now we need to somehow do that. Yikes. Okay, so how do we do that first piece up there? So first off, what's n? $70. So the frequency F, 12, times 0.06 squared plus. Do that for every row, right? So 15 times 0.09 squared plus. That's what that symbology means, okay? See? 14 times 0.12 squared plus 15 times 0.15 squared plus 14 times 0.18 squared. Close those parentheses. Whatever you get multiplied by 70, that's the first term of the numerator in your square root.
So really quickly. 12 times 0.06 squared plus 15 times 0.09 squared plus 14 times 0.12 squared plus 15 times 0.15 squared plus 14 times 0.18 squared. Blah. All of that work. To get 1.1574. Multiply by 70. That's the first term underneath the square root, right? The n times the sum of f times x squared. Now you have to do the other side, right? What is the sum of f times x, the whole thing squared? You're going to do almost the same thing, but slightly different, right? 12 times 0.06 plus 15 times 0.09 plus 14 times 0.12 plus 15 times 0.15 plus 14 times 0.18, and then when you're done with all of that sum, then square it. Now you see why it's so nice to use things like a spreadsheet program to work on this stuff. Because this is a pain in the ass to do it by hand, right? I mean, you can do it, it's just a pain. You guys get 8.52? And again, note that the denominator is n times n minus 1, so n was 70, n minus 1 is 69. And now it's just punch it in, right? 81.018 minus 72.5904 divided by, crap. Don't clear it, that would be bad. Divided by 70, divided by 69. And then take the square root of that.
Where would I round this number to? Where was our data? 2 decimal places. So where am I going to round to? 1 past. Always 1 past, right? So the standard deviation here is approximately 0.042. And I like to go over one of those because I do force you to do one of those on the homework. And it's basically me saying, can you look at this godforsaken formula and figure out how to make it work? All right? I know it's a little bit of a sort of like a sledgehammer question, and I apologize a little bit, but it's good for you. All right? All right, so. So I'm just going to touch on this a little bit right now. We'll come back to it in more detail in chapter 6. But the most common use for the standard deviation is when you were working in what we consider to be, as statisticians, normal curves. Normal curves, folks, are bell curves. Okay? So the idea behind a bell curve, folks, is that think of this as being some sort of a line graph for the frequency of a specific population. So things that are considered to be normal will often fit in a bell curve if you think about it in terms of its mean and its standard deviation. So one of the classic things that I like to talk about here is, say, shoe size. Okay? So the average shoe size of a full-grown man is like 10, right? Maybe it's somewhere between 10 and 11, right? So if shoe size for a male is normal, then it will fit into this curve. And the way it fits is that the very peak is where the average always sits. And so if you're thinking shoe size for full-grown men, this would be like 10 and a half or 11 or whatever it's going to be. The idea is that if you look at one standard deviation added and subtracted to the mean, one standard deviation in both directions, plus S and minus S, this will subdivide your bell curve into 68% of all men having shoe sizes that are between those two values, whatever they work out to be. So if the standard deviation of
a full-grown male is say 1.5, the idea is that when you add 1.5 up to 12 and subtract 1.5 down to 9, 68% of all men will have a shoe size between 9 and 12. Basically, 7 out of 10 of every man is going to have a shoe size between those two numbers. It's just, that's the way the statistics work, right? And when you add another standard deviation onto the outside, it's literally 95%. Right, 95% of all full-grown men have a shoe size between 7.5 and 13.5. And this is what drives companies working with standard deviations, right? Because if you're a shoe company, how many shoes are you going to make that are size 7? In fact, a lot of shoe companies don't make any size 7 shoe, because it's more than 2 standard deviations away, and only 2.5% of the population is actually going to potentially have the chance to wear that shoe. So why would they bother, right? And it's also the same way with anything that's normal, right? So body size. Our body sizes are all normal as well. If you're not within 2 standard deviations of the mean for your body size, guess what, folks? Yeah, you're shopping. It's tough for you to find clothes. And this is why. Because the statistics tell the business only sell to people that are going to buy the most of what you're selling. So find the averages and where most of the percentages are and work from there. All right? So this is why we care about standard deviation, because it does all of this calculation as a freebie. All right? So anyways, we'll get to more detail on that in chapter 6. Okay. All right, now, one. So, in the early to mid 1800s, he may be in the 1900s, Russian mathematician Chebyshev, brilliant statistician. Well, actually, he was more a mathematician than a statistician, but basically what he was trying to do was to do some analysis of numbers and averages, right? This is a little formula he dreamed up. And basically what it's saying is that there must be a certain percentage of all data that falls within a certain range of the mean and its standard deviation, right? So when k equals 2, that's k squared. So So what is 2 squared, folks? And what is 1 minus 1/4? So what Chebyshev's theorem, Chebyshev said was that 75% of all data must be in 2 standard deviations.
of the mean. In other words, you can't create data where more than 25% of your data is more than two standard deviations away from the mean. It's impossible. It was a really powerful theorem that basically led mathematicians to look at statistics and say, hey, wait a second, we actually can, using math, talk about what statistically is going on the planet. And it took a lot of work for Chebyshev to prove this. I'm not going to go into the details, but just basically know that that's out there, and it's a sort of a neat analysis to remind you that data can spread out, but as it spreads out, so does the standard deviation. And it always has to spread out such that for every 2 standard deviations, you engulf at least 75% of your data, which is a nice little trick. All right, so I just like to talk about that just for a second because I studied that for a while in graduate school. All right, so that is the end of section 2.2. All right. We're going back. Okay, so how many of you people have had kids? Have kids? Most of you? Half of you around? Okay, so one of the things that you will often hear doctors tell you is, oh, your child is in the 25th percentile, or the 80th percentile, or the 73rd percentile for height or weight or whatever, right? What do they mean? What does that mean? What does it mean to be in the 75th percentile for your weight or your height or whatever? Right, so it means that for your age, if you're in the 75th percentile, 75% of all the other kids are less than you, right? So if your height is, 32 centimeters at age, 1.5 or whatever, and you're in the 75th percentile, then 75% of everybody else at that same age will have a height that's less than you. That's what the 75th percentile means. So it's comparing it to everybody else that's at the exact same point in time as you are. All right? So, one of the things that we do when we're working with these sorts of percentiles, before we get there, is that we work with something called quartiles. That first root word, quart, it actually is really the root word for quarter. So quartiles are all the percentiles that you work with that are in a 1/4 break. Usually the quartiles we work with are these 3, because the 0th quartile, that just means your smallest number. And your 100% percentile is just your largest number. By definition, folks, the 50th percentile is the middle of the road. And we've already defined what that is. It's called the median, okay? So, the 25th percentile
since 25 is halfway between 0 and 50, the 25th percentile is the median of the lower half of the data. And the 75th percentile, guess what I'm going to call that? Yeah. And that's actually how you go about finding the 50th and the 75th percentile, or the 25th and the 75th percentile in a small sample size of data, is by simply saying, oh, find the median, and then find the median, and find the median again, right? So imagine, if you will, we have this information. So here's our data. 5, 6, 8, 9, 10, 12, 18, 19, 20, 21, 22. Let's not go too far. 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I already went too far. 23, 24, 25. Let's go there. Did I do 15 or 16? 15, okay. So find the 3 quartiles for this particular set of data. Find the 50th percentile, the 25th percentile, and the 75th percentile. These things have official names. The 25th percentile is often called the lower quartile, and the 75th percentile is often called the upper quartile. Just an additional name that goes with the number. So first things first here, folks, what is the median? How do you find the median again? Yeah, find the number in the middle. Which number is in the middle? 19, right? There's 7 here, 7 there, 19's in the middle. Okay. So now the lower quartile is the median of the lower half of your data. Well, nicely enough, here's the lower half from 5 to 18. What's the median of that set of data? That is your lower quartile. So it's one of those where you can kind of visually see what's going on, right? So what's the upper quartile? Which one's in the middle? 22. So that's kind of neat. I mean, it's sort of a nice trick to play or to look at and work with when you're dealing with quartiles, all right? Ah, not bad? Okay, so. All right, so. So how do I find the 40th percentile in this set of numbers? So the way you find a 40th percentile in a set of data
is look for that position's number. So, for us, 40th percentile, what was n again? 15. I'm looking for the 40th percentile, that goes into the p. What is 15 times 40 over 100? 6. When you are calculating your percentiles, if you get an exact number, what this means is that the 40th percentile is exactly the 6th number in your set, or the 40th percent is. Please remember that the 40th percentile means that at least 40% of your numbers are less than you are. Strictly less than, okay? So if the 6th number is the 40th percentile, 2, 3, 4, 5, 6, 12, are there 40% of my numbers less than 12? No, right, because the 12th number hits the 40th percentile. So is 10, 9, 8, 6, 5, 40% of your data? No, it's going to be less than 40%. It's going to be 1, 2, 3, 4, 5. 5 out of 15. What's 5 out of 15? A third, or 33%. So therefore, the 12th is not the actual, not actually the 40th percentile. The way you handle it is by calculating the average of the exact position you're at and the position after it. When this value is a whole number, then average this position with the next position. So for us, we're going to average the 6th and the 7th numbers. So my 6th number is a 12, my 7th number is an 18. What's the average of 12 and 18? So my 40th percentile for this data will be the value 15. And what that number means is that 15 is guaranteed to have 40% of the numbers less than it, because you know that 12 represents the 40th percentile. So if you just get past it, that guarantees 40% less than you, okay? That's the idea behind it. Now, if the number is not a whole number, so let's do like, let's use an odd number, say the 70th percentile. .5. Because this number has a decimal, the 70th percentile is at the 10.5th position. Therefore, we can just move up. And that will guarantee that 70% of my numbers are less than whatever position I am sitting in. So what's the 11th number? 15, 14, 13.
13, 12, 11. What did I say that was 21? So the 70th percentile would be a value of 21 for this set of data, all right? And that's what percentiles, or how you work with percentiles. Again, it's all based on what sort of data do you have and how you have to make sure that whatever percent you're looking at is less than the number that you give. You got to play around with it a little bit to really get it. So it's kind of cool to play around with it when you get a chance. And then the last thing that we have to talk about today. And these will become, again, more important in later days. Z-scores. Z-scores are basically just a normalized Z-score. We'll talk about what that means in chapter 6 when we get there. But I should be specific. Sample. Sort of the stuff you already know. We will be playing around with this heavily in chapter 6 when we get there. We have to play around with probability a little bit first. So the idea is, if x bar equals 10 and s equals 2, the z-score for x equals 4 is 4 minus 2 over 10. Except backwards. 4 minus 10 over 2. Can't even plug the right numbers in. 4 minus 10, negative 6. Take half of that. Negative 3. And we will learn what that negative 3 means in chapter 6. And I'll just ask you to calculate a couple of those on the homework, so I wanted to make sure you saw at least a quick sample before we move past it. All right. Not bad? A little bit funky. Some of this stuff is things that you've heard said to you over a time, and so hopefully I'm trying to clarify them a little bit. Maybe you get a chance to play around with them and see. So for next time, some of those will take a little bit of turning the crank calculation-wise. Please be ready. If you decide to use some sort of a spreadsheet program to do these, please make sure that you print out all of your data as well as your answers so that I can see what you put in to make it work, okay? So don't just write the answer into a cell in Excel and then print that one box. Show me all of your data so that I can see how you calculated the numbers that you are calculating, okay? Here's all my homework. Awesome. That chapter can be a little heavy sometimes. It gets a little data intensive.